morning, everybody. This is Dr. M. Satyanarayana Gupta, Professor and HOD, Department of Aeronautical Engineering, MLR Institute of Technology. So, last class we discussed about the introduction of finite element method. There I discussed about the finite element procedure and the finite element advantages, disadvantages and applications of FEM. So, after that, today I will discuss about the elasticity equations. So, in this elasticity equation, first I will discuss about the relation between strain and displacement. So, last class already I said that using the finite element method, we find the displacement. Displacement is a field variable for the static analysis. Once you find the displacement as engineer for any analysis, we have to calculate the strain. To get the strain, we have to develop the relation between the strain and displacement. So, using these relations, we will find the strain if you know the nodal displacements. So, to find the strain, first I will discuss the relation between the three-dimensional body. So, once we can know about all the strain components of three-dimensional body, then we will see the two-dimensional body and one-dimensional body. So, the three-dimensional body contains the 6 stress components. Those are epsilon x, epsilon y, epsilon z, and epsilon xy, epsilon xz, and epsilon yz. So, here epsilon x means it is a strain in x direction. Epsilon y means it is a strain in y direction. Epsilon z means it is a strain in z direction. And epsilon xy, epsilon xz, and epsilon yz are the shear strains. And see, in this one, the first 3 components are normal strains and next 3 components are shear strains. So, first 3 are these we can call as a normal strains. You already know about the normal strain means when it is induced, when this force is acting perpendicular to the failure area. And you also know that what is the shear strain. Next 3 are the shear strains. So, shear strain means the load will be act parallel to the failure area. Then the shear strains will be induced. So, there are 3 shear strains, that is epsilon xy, epsilon xz, and epsilon yz. Now, we will see the one by one. So, first we can see the epsilon x, that is a strain in x direction. So, you know that any engineering analysis, our analysis will start with the differential dimensions. So, to get the strain in x direction, I will take the differential length of the bar or rod. So, it is a differential length. So, I am taking a dou x. So, the length of this bar, initial bar is a dou x when it is subjected to the axial load, subjected to this a load F, axial load, or it will subjected to the differential load delta F. It will be deformed in the x direction. How much it will be deformed? It will be deformed in the dou u. Here dou u means here u is a displacement in x direction. So, u is a, suppose you take the u equal to displacement in x direction, and dou u is a differential displacement in x direction. So, here if a differential length of the bar dou x is subjected to the differential load dou f, then it will be deformed to the differential length, that is a dou u. Here u is a displacement in x direction. Then we know that the strain equal to change in length by original length, otherwise change in dimension by original dimension. Here change in length is a dou u and original length is a dou x, then epsilon x equal to dou u by dou x. So, the strain in x direction, is dou u by dou x. Similarly, if you take the y direction, then suppose say v is a displacement in y direction. So, v is displacement in y direction. V is a displacement in y direction. Then epsilon y equal to dou v by dou y. So, here dou y is a original length in y direction. V is a displacement in the y direction. Dou v is a differential displacement in the y direction. Then the strain in y direction epsilon y equal to dou v by dou x. Similarly, if you take what is called epsilon z, and W is a displacement in z direction, so epsilon z equal to dou W by dou z. Here dou z is a differential length in the z direction, and W is a displacement in the z direction, then the strain in the z direction is dou W by dou z. So these three are the what is called normal strain. Now we jump into the what is shear strain. So in this shear strain, first we will take the epsilon xy. So to derive the epsilon xy, let us take a body A, B, C, D. So it is an undeformed body. So already I said that in shear strain means the load will be act parallel to the failure area, otherwise tangential load will be act on the body. Suppose load is acting in this direction, that means parallel to the failure area, then the body will be deformed like this. So this is a deformed body. So let us take the deformed body is A dash, B dash, C dash and D dash. So here A, B, C, D is a undeformed body. A, B dash, C dash, D dash is a deformed body. So I already said that for any engineering analysis, we need to take the differential dimensions. Here also, the side of the square or rectangle ABCD, we will take, I taken as a differential length in y direction. That means AD equal to dou y. In horizontal, AB equal to dou x. So these are the differential dimensions of the body. And see, if you see the deformation, so in y direction, so dou x will be deformed in y direction by dou v. So deformation, so dou x is deformed in the y direction, that I am taking as a dou v. That means v is a deformation in the y direction, dou v is a differential deformation in the y direction. Why? Because our original length is a dou x, that is a differential length. Similarly, so dou y is deformed horizontally. So this is I am taking as a what is called dou u. So here dou x and dou y will be deformed as a dou v and dou x. Then once again, epsilon xy, based on the definition of the shear strain, epsilon xy equal to, you take the x direction, this is a dou v by dou x, and if you take the y direction, dou u by dou y. So epsilon xy, the shear strain epsilon xy equal to dou v by dou x plus dou u by dou y. So epsilon xy equal to dou v by dou x, dou u by dou y. Here dou x and dou y are the sides of the body, differential lengths of the body, and dou v, dou u are the differential deformations. And similarly, if you take what is called epsilon xy, then we have the shear strain epsilon xy equal to dou w by dou x plus dou u by dou z, and the last one similarly epsilon yz equal to dou w by dou y plus dou v by dou z. So here you have to observe one thing is the deformation is in y direction, but the length is in x direction. Similarly here deformation is in x direction, but length we consider in the y direction. So in shear strain, these will be swapped. So this is the relation between the strain and displacements. So here u, v, w are the displacements in x, y, z directions respectively, and we have the 6 strain components. 3 is normal strains and 3 is the shear strains. Here one more thing you have to remember is the shear strain epsilon xy is equal to the epsilon yx, and similarly epsilon xz is equal to the epsilon zx, and epsilon yz equal to the epsilon zy. So next we can go with the two-dimensional body. So in two-dimensional body, the all z components becomes 0. So we take the previous one only, three-dimensional body. In the three-dimensional body, all z components will becomes 0. That means epsilon z equal to 0, and epsilon xz equal to 0, and epsilon yz equal to 0. Then the remaining one will be used the strain and displacement relations between the two-dimensional body. So here you see that this is the two-dimensional body have the 2 normal strains and 1 shear strain. So it is same as what is called in previous derivation. So there all z components become 0 if we come with the 2D. That means in three-dimensional body, if you can keep the epsilon z equal to 0, epsilon xz equal to epsilon yz equal to 0, then we will get the strain and displacement relations for the three-dimensional body. The remaining three are the epsilon x, epsilon y, and epsilon xy. And already I discussed epsilon x equal to dou u by dou x, and epsilon y equal to dou v by dou y, and epsilon xy equal to dou v by dou x and dou u by dou y. And coming to the next, one-dimensional body. So if the one-dimensional body subjected to the load, then you have the y components also become 0. So the y components means epsilon y equal to 0 and epsilon xy also equal to 0 in previous equation, in above equation. So if epsilon y equal to 0, epsilon xy equal to 0, we have the only remaining one is a epsilon x. So in one dimensional, we have the only one strain component, that is epsilon. We can simply call as a epsilon. Otherwise, we take as a epsilon equal to epsilon x equal to dou u by dou x. So that means if you take the three-dimensional body, we have the 6 strain components. The two-dimensional body, we have the 3 strain components. If it is a one-dimensional body, we have the only one strain component. Now we can go with the one numerical problem. So if a displacement field is described as u equal to minus x square plus 2y square plus 6xy into 10 to the power of minus 4, and the displacement in y direction v equal to 3x plus 6y minus y square into 10 to the power of minus 4, determine the components, that means strain components epsilon xx, epsilon yy and epsilon xy at a point x equal to 1 and y equal to 1. We read this problem. So they given the displacement in x direction, that is u, and the displacement in y direction, that is a v, and also they are asking that the condition is we need to calculate the all strain components in the x equal to 1 and y equal to 1. At that point we have to calculate. So here the problem, it is given that u equal to minus x square plus 2y square plus 6xy, and we also know that the strain in x direction equal to epsilon x equal to or epsilon xx equal to dou u by dou x. That means differentiate above equation, otherwise differentiate equation u with respect to x. So if differentiate the above equation with respect to x means, so the 2y square means there is a no x coordinate here, so it becomes 0. And also you know that the differentiation of the x to the power of n equal to n into x to the power of n minus. That means say dou by dou x of x to the power of n equal to n into x to the power of n minus 1. So same thing you apply here, then minus 2x square becomes minus 2x plus 6xy. If differentiate with respect to x, then you will get what is called xy into 10 to the power of minus 4. That means if differentiate above equation with respect to x, we will get the minus 2x plus 6y into 10 to the power of minus 1. And this is a strain in x direction, but it is also given that we need to calculate the strain at a point x equal to 1 and y equal to 1. So substitute above equation x equal to 1 and y equal to 1. That means minus 2 into 1 plus 6 into 1 into 10 to the power of minus 4. That means you substitute the values. So minus 2 into, you substitute x equal to 1, and next is 6 into the y equal to 1. So this equal to 6 minus 2, that is a 4 into 10 to the power of minus 4 is a strain in x direction. So the strain in x direction equal to 4 into 10 to the power of minus 4. And next, similarly, they are also asking find the strain component in y direction. We know that the strain component in y direction equal to v equal to 3x plus 6y minus y. It is given in the problem only. So now we also know that the formula for epsilon yy equal to dou v by dou x. Just now I derived this one. So this equal to, you have to differentiate the above equation with respect to y. Whenever you differentiate with respect to y, so the 3x is there is a no y coordinate, so it becomes 0. The remaining one, I already said that say dou by dou x of x to the power of n equal to n into x to the power of n minus 1. Same formula you apply here. So the 6y becomes 6. The differentiation of 6y is a 6 minus differentiation of 2y square means it is a 2y. So finally epsilon xy equal to 6 minus 2y into 10 to the power of minus 4. And this strain also we need to find out at a x equal to 1 and y equal to 1. So substitute in above equation x equal to 1 and y equal to 1. So then this is a 6 minus, here 6 minus 2 into 1. So you have to substitute y equal to 1 means, so it is epsilon yy equal to 6 minus 2 into 1 into 10 to the power of minus 4. Then it is becomes 4 into 10 to the power of minus 4. That means the strain in the y direction epsilon yy or epsilon y equal to 4 into 10 to the power of minus 4. And the last component is epsilon xy. So epsilon xy is a shear strain. I already discussed about this, what is shear strain. So this equal to dou u by dou y plus dou v by dou x. So same equation number A and B, but we have to differentiate with respect to other variables. So epsilon xy equal to dou u by dou y. So the equation number A gives the u, differentiate equation number A with respect to y. So whenever I differentiate the equation number A with respect to y means the x, there is a no y coordinate here. So if differentiate minus x square, it becomes 0. And next say you apply the same formula, 2y square becomes 4y plus 6xy. If differentiate with respect to y, then it is becomes 6x. So that means dou u by dou y equal to 4y plus 6x into 10 to the power of minus 4. Next is dou v by dou x plus dou v by dou x. So equation number B gives the v, it is given in the problem only. If you differentiate the v with respect to x, if differentiate this one with respect to x means, so the 6y is a constant, so it becomes 0. Why? Because there is no x coordinate. And the other terms, just you apply the same formula. So then 3x, the differentiation of 3x is a 3 and the differentiation of minus y square is a minus 2y. So dou v by dou x equal to 3 into 10 to the power of minus 4. So then epsilon xy equal to, you substitute the x equal to 1 and y equal to 1 in our equation, then you will get the epsilon xy equal to 4 into 1 plus 6 into 1 into 10 to the power of minus 4 plus 3 into 10 to the power of minus 4. Then it is a 10 plus 3. So it becomes epsilon xy equal to 13 into 10 to the power of minus 4. So this is a simple problem on relation between the strain and displacement. So in this problem, they given the displacement equations. So using those equations, we find the strain components at a given point. The given point is x equal to 1 and y equal to 1. So here I am stopping today. So tomorrow we will discuss about the other elasticity relations. Thank you. Thank you one and all.